Linear equations in two variables. The Cartesian coordinate system consists of two intersecting lines. The horizontal line is called the x-axis, and the vertical line is called the y-axis. The point where the two axes intersect is called the origin, and is described by the ordered pair 0, 0. Every other point in the Cartesian coordinate system is also described by an ordered pair consisting of an x value and a y value. The x value tells us to move left or right depending on the sign of the number, and the y value tells us to move up or down, again depending on the sign of the number. So consider this point located right here. Starting at the origin, to get to that point using horizontal and vertical movement, we would need to move right 8 units, meaning that our x value in our ordered pair is an 8. And then we would need to move from there down 4, meaning that our y value is a -4. The point located on the x-axis is also described by an ordered pair in which we move 3 units to the right of the origin. And then since we do not move up nor down from there, our y value is simply 0. The point located a little higher than that can be described by an ordered pair. To get to that location from the origin, we would move right 6 units, so our x value is 6. And then from there, we would move up 9 units, making our y value 9. This point, located in the second quadrant, is determined by the ordered pair -6, since we moved to the left of the origin, +3, since we move up from there. One other point that's given on our Cartesian coordinate system is described by the ordered pair -10 for the x value, since we had to move 10 units in the negative direction to the left. And then since from there we move down 2, our y value is a -2. A linear equation in two variables is an equation that describes an infinite set of ordered pairs. In example 1, we're given the linear equation x plus y equals 6, and we're asked to complete a table of ordered pairs for various values of x and y. So in our first row of our table, we're told that x equals 0. So replacing the x in the original equation by 0 and solving for y, we find out that y equals 6. And notice that 0 plus 6 does equal 6, as we want it to in the equation. In our second row, we're told that y equals 0. So replacing y with a 0 and solving for x, we get x equals 6. And again, checking this out, 6 plus 0 does give us the 6 that we want in our equation. In the next row, we're told to replace x with the number 1. So now we have the equation 1 plus y equals 6. And subtracting 1 from both sides to solve for y, we find out that y equals 5. And notice that 1 plus 5 does equal the 6 that we need it to. Finally, in the last row, we're told that y is being replaced by 3. So replacing y by 3 and subtracting 3 from both sides of the equation, we find that x equals 3. And again, notice 3 plus 3 does equal 6. Now, our table only has 4 ordered pairs in the table, but keep in mind that this linear equation in 2 variables describes an infinite set of ordered pairs. That is, there are many pairs of numbers whose sum equals 6. The graph of a linear equation in 2 variables is a straight line. Reconsider the equation x plus y equals 6. In the previous example, we completed a table of values that gave us 4 ordered pairs, 0, 6, 6, 0, 1, 5, and 3, 3. Remember, this was just a small sample of the ordered pairs that satisfy this equation. There are infinitely many ordered pairs whose coordinates sum to 6. But plotting these 4 points on our Cartesian plane, we see that they lie in a line. And these are not the only 4 points that lie on this line. There are an infinite number of points that describe this particular equation. Y equals mx plus b is called the slope-intercept form of the equation of a line, where m represents the slope, m being the coefficient in front of x, and b representing the y value in the y-intercept, where b is the constant term being added to the x term. The y-intercept is the point where the graph crosses the y-axis, and that is why the x value in that point is 0. So consider example 3, where we go back to the equation x plus y equals 6. We are asked to write this equation in slope-intercept form, and then determine the slope and the y-intercept of the line. To get this equation in slope-intercept form, we must solve for y. So subtracting x from both sides, we get y equals negative x plus 6. So comparing this to the slope-intercept form, which is y equals mx plus b, we can see that the number in front of x is a negative 1, which means that our slope is a negative 1, and the constant term being added to that x term is a 6. So the y-intercept is the point 0, 6, since it lies on the y-axis, and the y-intercept then occurs at the value y equals 6. In example 4, we continue to examine the equation y equals negative x plus 6. In writing our equation for our line in this form, we can identify the slope, and in this example, the slope is a negative 1, and we can identify our y-intercept. In this example, our y-intercept is the ordered pair 0, 6. Recall, the y-intercept is the point where the graph crosses the y-axis. So in this case, our graph crosses the y-axis at 6. Now, in order to identify at least one additional point so that we can draw our line, we need to use our slope. Our slope is indicated by m. If we can write our slope as a fraction, then we can determine a second point by starting at our y-intercept in this case, and then moving up or down, depending on the sign of the numerator, and then moving left or right, as indicated by the denominator. So looking at our slope of negative 1 and rewriting it as negative 1 over 1, we can see that our rise is a negative 1 and our run is a positive 1. This tells us that we start at our y-intercept and we move down 1, since our rise is negative 1, and we move right 1, since our run is positive. After making those two movements according to our slope, we can plot a second point. And furthermore, we can continue this process indefinitely until we have enough points to satisfy our needs. So this means that we can continue from our new point, moving down 1 because our rise is negative 1, and right 1 since our run is positive. So in doing that, we end up with a third point at 2, 4. And all of these points that I've plotted lie on the same line that we saw in example 2. In example 5, we consider a new equation, y equals 3x minus 5. Notice that our linear equation in two variables is written in the slope-intercept form. So that means we can identify the slope. In this case, the slope equals 3. And we can identify the y-intercept. In this case, our y-intercept is 0, negative 5. That means that our line passes through the y-axis where y equals negative 5. Now we need to rewrite our slope so that we can use it to locate at least one additional point. So writing our slope as a fraction, 3 over 1, the numerator tells us our rise, our denominator tells us our run. So starting at our y-intercept, we're going to rise a positive 3, which means we move up 3, and then move 1 to the right, since it's a positive. After making those two movements, we plot a new point at 1, negative 2. Repeating this process from there, up 3, right 1, we have a second point, or a third point rather, at 2, 1. And now we have a line. We can draw a line through those points. And we have our graph. In example 6, we're considering the equation y equals negative 1/4 x minus 2. The negative 1/4 tells us our slope, and the minus 2 gives us the y value of our y-intercept. So plotting our point at 0, -2, we now use our slope to determine additional points. The numerator of our slope gives us our rise. Since it's negative, that tells us from our y-intercept we're going to move down 1. Since our denominator is positive, our run will be to the right 4 units, locating a second point on our line at 4, -3. Repeating from there, down 1, right 4, we find a third point at 8, -4. And now we can sketch our line. One other comment about the slope. The negative sign can be placed in the denominator instead of the numerator. In other words, instead of writing -1/4, we can write 1 over -4. And if this is the case, notice that our rise is no longer negative. So we will be moving up. So starting at our y-intercept and moving up 1. Our run is now the negative value. So instead of running to the right, like we did before, we're going to run to the left 4. And in doing that, we find another point on our line. Determining the slope. Recall that a linear equation in 2 variables is an equation that describes an infinite set of ordered pairs. Furthermore, the graph of a linear equation is a line. In example 1, we're given the linear equation 5x plus 2y equals 6, and we're asked to complete the table of ordered pairs that satisfy that equation. When we look at the first row in our table, we see that we're given a partial ordered pair. That is, we're told that x equals 0, and we're wanting to determine the corresponding y value. So we go to our equation and we replace x with the 0 that we're given. Our equation now only has the variable y. So we can now determine what y value corresponds with x equal to 0. 5 times 0 is 0. So rewriting our equation, after doing that product, we get 2y equals 6. Dividing both sides by 2 tells us that y must equal 3. Now we have a complete ordered pair. In the second row, we have another partial ordered pair, but this time we need to determine the x value that corresponds to a y value of -7. This time we replace the y value with the given value in our table, and we solve for x. Notice that 2 times -7 is a -14, so we can rewrite our equation as 5x minus 14 equals 6. Now we solve for x. Add 14 to both sides, which results in 5x equals 20, and then divide both sides by 5. So we find out that x must equal 4. And now we have a second complete ordered pair. In our third row of our table, we're told that x equals 1, and we need to determine the y value that corresponds to that x value. So replacing x in our equation by 1, 5 times 1 is 5, so rewriting, and now solving for y by first subtracting 5 from both sides, and then dividing both sides by 2, results in y equaling 1/2. And remember, these 3 ordered pairs are only 3 of an infinite set of ordered pairs that are described by this particular linear equation. In our previous example, we determined 3 ordered pairs that lie on the line that corresponds to the graph of 5x plus 2y equals 6. 2 of those points are denoted in this graph below. In example 2, we're asked to determine the slope of this line. If you can identify 2 points on your line, preferably integer-valued points, you can easily determine the slope by looking at the vertical and horizontal movement necessary to get from one point to the other. For example, given the 2 points on our line, if I want to move from the point located at 0, 3 and end up at the second point noted on our line, 4, -7, to get from the 0, 3 to the 4, -7 using only vertical and horizontal movement, we would need to move down 10 units and right 4 units. The 10 represents what we call rise, the vertical movement. The 4 represents what we call run, the horizontal movement. The slope is determined by the rise over the run. Another way to think about slope, if you don't have the actual line, but you do have 2 points given to you, is to use the formula above. So let's go ahead and try using that formula and then relate it back to our graph. So let's identify the point 0, 3 as x sub 1, y sub 1. And let's denote 4, -7 as x sub 2, y sub 2. According to the slope formula, we take the difference in the y values, y sub 2 minus y sub 1. So we have -7 minus 3, divided by the difference in the x values, x sub 2 minus x sub 1. So we have 4 minus 0. Notice that it's very important that the order in which you subtract is the same in the numerator and the denominator. That is, we have y sub 2 minus y sub 1 in the numerator and x sub 2 minus x sub 1 in the denominator. You don't want to mix the order in which you subtract. So when we do the arithmetic now, -7 minus 3 gives us -10. 4 minus 0 gives us 4. And notice that's exactly the same numbers that we obtained from our graph when we looked at the rise and the run. Notice also that this particular fraction can be simplified by dividing numerator and denominator by the common factor of 2. So our slope in simplified form is -5/2. One other comment: if I had used two different ordered pairs in my graph, I would obtain the same slope. Consider using 0, 3, and instead of 4, -7, since I see a nice integer valued point at 2, -2, if I had chosen to use that point as my x sub 2, y sub 2, I would get the same slope. Checking that with our graph, we see that to move from 0, 3 to 2, -2, we would still need to move down 5. But then we would be moving over to the right 2. So notice what we did. We had a rise of -5 since we moved down, and we moved to the right 2, which is the same slope as what we got when we used the other 2 points. In example 3, we're asked to determine the slope of the line passing through 2 given points. Notice this time we do not have a graph. However, we can still determine the slope by using the slope formula noted above. So let's begin by identifying which point will represent x sub 1, y sub 1, and which point will represent x sub 2, y sub 2. Once you've identified your 2 points, then it's a matter of replacing the variables with the numerical values. So our numerator is the rise or the change in the y values. So we have 17 minus our -11. And our denominator is the difference in our x values. So here we have 18 minus a -6. Remember, when you subtract a negative, that's the same as addition. So in the numerator, we have 28. In the denominator, subtracting a negative results in 24. We always want to simplify our slope. So notice there is a common factor of 4. Dividing numerator and denominator by that common factor gives us a final slope of 7/6. In example 4, we're asked to determine the slope of a line passing through 2 given points and then graph the line. So we begin by identifying x sub 1 and y sub 1, x sub 2 and y sub 2. Placing the numerical values in the appropriate location in our formula, we have that the numerator is -5 minus a -5, and the denominator is 3 minus a -1. When we subtract a negative, that becomes addition. So our numerator is now -5 plus 5, or 0. In the denominator, we end up with 3 plus 1, or 4. 0 divided by 4 is 0. So we have found that the line that passes through these 2 given points has a slope of 0. What does our graph look like? Let's plot our 2 points and see. So we have -1, -5, and 3, -5. Our line passes through those 2 points, and it turns out that our line is horizontal. So we can conclude here that horizontal lines have slope 0. That is, they are flat. Example 5 also asks us to determine the slope of the line passing through 2 points and then graph the line. So we begin by identifying our 2 points so that we can make sure we place the numbers in the appropriate places in the formula. Our numerator, based on our determination of our points, will be 3 minus 0, and our denominator is 4 minus 4. Performing the operations, we have 3 over 0. But 3 divided by 0 is undefined. If we tried to divide 3 by 0 on a calculator, it gives us an error. Let's graph this line and see what our sketch looks like. So we plot our point 4, 0 and our point 4, 3, and we draw our line that passes through those 2 points, and we see that we have a vertical line. So we have a conclusion here. Vertical lines have undefined slope. There is no run for a vertical line. It's strictly rising or falling. Horizontal and vertical lines. Horizontal and vertical lines have special equations. Consider this horizontal line in example 1. If we were to make a t-table that provided us with ordered pairs that appear on that horizontal line, let's see what they would have in common. For example, there's a point located at 0, 5 on that horizontal line. There's also a point located at 4, 5 on that horizontal line. And there's a point at -9, 5 on that horizontal line. In fact, there are infinitely many points on that horizontal line that all have a y value of 5. Therefore, the equation for this horizontal line is simply y equals 5. X can be anything. Similarly, consider this vertical line. Going to our t-table and identifying the ordered pairs to go along with the points on that vertical line, we see that there is a point at -2, 0. There is a point at -2, -6. There's a point at -2, 1. But notice there are infinitely many points that all have the x value of -2. Therefore, the equation for this vertical line is x equals -2. Intercepts. Recall that the y-intercept is the point where a graph crosses the y-axis. Similarly, the x-intercept is the point where a graph crosses the x-axis. So consider example 1 in which we're given the sketch of a line. Notice that our line crosses the y-axis at 0, -2. That particular point is our y-intercept. Notice that at our y-intercept, the x value is 0. Now notice also that this graph crosses the x-axis at 5, 0. That particular point is called our x-intercept. Notice that the y value of our x-intercept is 0. In example 2, we're asked to determine the x and y intercepts of the graph of a line, but we're not given the graph. Instead, we're given the equation. This means that we must use algebra to determine the x and y intercepts. Beginning with the x-intercept, recall that the x-intercepts occurred where the y value equals 0. So replacing y in our original equation with 0, we then solve the equation for x. And we do this by adding 12 to both sides, resulting in 12 equals negative 4x, and then dividing both sides by negative 4. Resulting in x equals negative 3. So the x-intercept occurs where y equals 0 and x equals negative 3. Similarly, for the y-intercept, recall that those points occur where x equals 0. Since we're on the y-axis, the x value is 0. So going to our original equation and replacing x with 0, we have y equals 0 minus 12, or y equals a negative 12, telling us that our y-intercept occurs where x equals 0 and y equals negative 12. Example 3 also asks us to determine the x and y intercepts of the graph of a line given an equation. So recall, to find the x-intercepts, we let y equal 0. Going to our equation and replacing our y with 0 results in x equals 0 plus 8, or x equals 8, telling us that the x-intercept occurs where y equals 0 and x equals 8. Now considering the y-intercept, which is found where x equals 0, we go to our original equation and we replace x with 0, and we solve the resulting equation for y. We do this by subtracting 8 from both sides, giving us negative 8 equals 6y, and then dividing both sides by 6. Resulting in y equals negative 8 sixths, which can be simplified by dividing numerator and denominator by the common factor of 2, resulting in negative 4/3. So our y-intercept occurs where x equals 0 and y equals negative 4/3. Exponential equations. In this video, we take a look at the exponential equation. Consider example 1, in which we're asked to complete the table of ordered pairs that satisfy the exponential equation y equals 5 raised to the x power. Suppose x equals negative 1. Replacing x in the equation with a negative 1, we have y equals 5 to the negative 1 power. There is a property of exponents that will help us to rewrite this so that our answer is a little bit more meaningful to us. That is, if you have a negative exponent, you can rewrite your expression without the negative exponent by moving that expression to the opposite side of the fraction that it currently is located. So that would mean that we would then have 1 over 5 to the positive 1 power. After the movement to the other side of the fraction, the exponent becomes positive. So if x equals negative 1, our y equals 1/5. Now suppose x equals 0. Replacing x with 0 gives us y equals 5 to the 0 power. And according to a second property of exponents, a non-zero number raised to a 0 exponent results in 1. If x equals 1, replacing the x with 1 gives us y equals 5. And if x equals 2, replacing the x with a 2 gives us y equals 5 squared, or 25. Now in example 1, we came up with a set of ordered pairs to correspond with the exponential equation y equals 5 to the x power. That table of ordered pairs is repeated on this slide. In example 2, we're asked to graph this equation. So let's plot these points that we found in example 1. We have a point at negative 1, 1/5, which is very, very close to the x-axis. We have 0, 1, which is just a little bit higher. We have 1, 5, and we have 2, 25. Notice that our equation increases as we move from left to right. Notice also that the graph on the left approaches the x-axis and doesn't actually touch it. We call the x-axis in this case an asymptote. We also say that this particular graph models growth, in that as we move from left to right, the graph increases. From left to right, the graph increases. In example 3, we graph the exponential equation y equals 3 to the x power. Notice that the graph of y equals 5 to the x power is still on our coordinate system, so that we can see how reducing our base from 5 to 3 changes our graph. So let's complete the table. When x equals negative 1, y equals 3 to the negative 1 power, or 1/3. When x equals 0, y equals 3 to the 0 power, or 1. When x equals 1, y equals 3 to the first power, or 3. And finally, when x equals 2, y equals 3 squared, or 9. Plotting the points that correspond to these ordered pairs, we have a point at negative 1, 1/3, 0, 1, 1, 3, and 2, 9. Notice that as we move from left to right, our graph increases, just as it did with the graph of y equals 5 to the x power. Notice that it did not increase as quickly as y equals 5 to the x, but it still was increasing. So, generalizing, when you have an exponential equation of the form y equals a to the x power, notice that you have to have it raised to the x power. If your a, your base, is bigger than 1, then your graph will model growth. The larger the base, the more quickly it grows, and the more steep the graph becomes. Regardless, there is an asymptote that is equal to the x-axis. In example 4, we graph the exponential equation y equals 3 to the negative x power. Notice that the exponent is now a negative x. That is different from the graph of y equals 3 to the positive x that we saw in the previous example. So notice that the graph of y equals 3 to the x power remains on our coordinate system so that we can see how changing that exponent to a negative x impacts our graph. When x equals negative 2, we have y equals 3 to the opposite of negative 2. The double negative causes our exponent to become a positive 2, resulting in 3 squared, or 9. When x equals negative 1, we have y equals 3 to the opposite of negative 1. Again, our exponent becomes positive because of the double negative, and we have y equals 3 to the first power, or just 3. When x equals 0, we have 3 to the 0 power, which equals 1. And when x equals 1, we have 3 to the negative 1 power, which gives us 1/3. Plotting the points that correspond to these ordered pairs, we have a point at negative 2, 9, negative 1, 3, 0, 1, and 1, 1/3. Notice as we move from left to right, our graph decreases. So when our exponent is a negative x, we see what we call decay. As we move from left to right, our graph decreases and approaches an asymptote that is equal to the x-axis. In example 5, we graph the exponential equation y equals 1/3 to the x power. Notice that in this example, our base is a unit fraction. That is, the 1/3 lies between 0 and 1. Notice also that our exponent is x, not negative x, like was seen in example 4. However, the graph of y equals 3 to the negative x is still on our coordinate system from example 4, so that we can see how these two equations are similar. So now let's complete the table for the graph of y equals 1/3 to the x. When x equals negative 2, we find that y equals 1/3 to the negative 2 power. And according to the property of exponents above, we can rewrite this as 3 to the positive 2 power, or 9. So notice, if we have a unit fraction such as 1/3 raised to a negative power, the denominator of the fraction comes to the numerator and the exponent becomes positive. When y equals -1, we have y equals 1/3 to the negative 1 power. And according to the property of exponents above, this can be rewritten as 3 to the positive 1 power, which is just 3. When x equals 0, we have y equals 1/3 to the 0 power, which is just 1. And when x equals 1, we have y equals 1/3 to the first power, or just 1/3. Plotting the points that correspond to these ordered pairs, we have a point at -2, 9, -1, 3, 0, 1, and 1, 1/3. All 4 points lie directly on the graph of y equals 3 to the negative x. In fact, every point on the graph of y equals 3 to the negative x is also on the graph of y equals 1/3 to the x power. This tells us that these two equations represent the same graph. This also tells us that if we have an equation in the form a to the x, not a to the negative x, rather a to the x, and if our base is a unit fraction, that is between 0 and 1, then we know that our graph will model exponential decay. That is, the graph will decrease as we move from left to right towards a horizontal asymptote that is the x-axis. Interpreting graphs. In example 1, we're given the graph of a line and an exponential curve, and we're asked to determine the interval of x over which the graph of the line is above the graph of the exponential curve. Above the graph means higher than the graph. So notice that the line is above the exponential curve in between the 2 points where they intersect. Now what we need to do is describe the interval of x over which this happens. So dropping down to the x-axis from those endpoints, we see that the left endpoint has an x value of a, and the right endpoint has an x value of c. And for all the x values in between, the line is above the graph of the exponential curve. So the interval of x, where the line is above the exponential curve, is the interval from a to c, not including those endpoints, because the instructions say express final answer as an open interval. In example 2, it asks us over what interval of x is the graph of the line below the graph of the exponential curve. So notice that the line is below the exponential curve to the right of this point where x is b. and to the left of this point where x is d. So we now want to describe these intervals going in opposite directions. So the open interval to the left starts at -infinity and goes to the right towards d. Union that with the other interval that starts at b and moving to the right, going off to infinity. Those two intervals together answer the question, over what interval of x is the graph of the line below the graph of the exponential curve?